Hi, I'm back. Yeah, so that was actually my baby calling just for my snaps and my health insurance and whatnot. So it's good. And I wasn't expecting them to call me so soon because I did all this today, and I was procrastinating on that because I've been so busy with other things and thinking about physics and shit. Which yeah, I mean I try to do things as I'm thinking about them because I'm the kind of person to forget if I don't write it down somewhere. Because I'm just so I have a one-track mind. I get engrossed in things, and it happens to be this right now, and anything outside of the thing that I'm focusing on right now is not necessarily that interesting to me, or happens to be something that my mind isn't really thinking about. And sometimes it comes back into my head, but then most of the time when it comes back, I'm like, nah, I'm too busy worrying about this instead of actually just getting it out of the way and then going back to it. I don't think I'm inherently a bad multitasker. Maybe I am. Just because I haven't practiced, well, multitasking is kind of a myth, but I believe that my multitasking capabilities are bad because my brain has atrophied from me being so obsessive towards certain topics as opposed to, doing things in unison or in parallel with each other and whatnot. So I don't know. Maybe. I actually don't remember. Maybe I am a bad multitasker because I don't quite remember what I was kind of talking about other than like some complicated stuff involving a full theory of the of everything basically that can encapsulate basically what physics is trying to get to, which is coming up with a unified field theory, and they're having a lot of trouble with it. And yeah, I don't know. I was also looking at Unzicker. What's his name? Unzicker. He's a physics guy. He has a YouTube channel, and I think he's German or something. And he just he seems to be talking about like the mistakes that physicists have made in the past and whatnot, and how there are a lot of things that we kind of just like threw under the rug. Like, well, one of them being renormalization in quantum electrodynamics. Feynman believed that was one of the only ways that they could deal with infinitesimals and infinities, basically, because I mean there's an inverse relationship between an infinitesimal. If the infinitesimal is at the bottom or the denominator, then obviously it's going to be an infinity. And the reason why that these infinitesimals are at the there's like a dA involved with everything. Like when you think about energy, right? You have a let's say this is a finite amount of area, and then you have a certain amount of energy there. But there's as you zoom in okay, what's a good way to think of it? You can think of like energy being imposed in one area, but also when you look at that, there's a point energy, quote unquote point energy. It's not necessarily a point energy, but we would call it that. And I think what Feynman had wrong was that he was, what would be a good way to say this? I think it's because we just distribute information outwards, and then when we try to compactify it into an infinitesimal, obviously, then it would blow up because it's the infinitesimal is a dA, and that goes up, and obviously the energy is depending on that. It's E per dA, the density of, I guess that would be another way, it's the density of energy per dA times n, because you have to have the n there divided by the dA. So, or you could just have the density of energy times a big N, and that density of energy is dA, delta A, whatever. And as that dA gets smaller and smaller, the density gets bigger and bigger, obviously, because the area is changing, but it's still that energy contained within that point, and then you have it multiplied by an n. So, which is interesting to think about, but I don't know. I don't feel like thinking about it right now. Yeah. Yeah, I guess the density can also be seen as you could also take the change of density, because yeah, you can take the derivative of the density and all that, and maybe if you take the derivative of the density, that would also go up because again, it's an EDA, and then I don't know. I think of like an E over dA is just dE, a small, very I guess it's a D E dA, I guess. That's a change of energy with respect to the area. So there's a certain amount of energy change with the area change, infinitesimal area change. So, and of course you have to do that because you're looking at a total area and whatnot, and there's times an n associated with it. But then you could actually just turn that into an integral. Yeah, I don't know. I don't really think about analysis as much as I used to. But yeah, from on the board, and I probably had some kind of monologue, but then I just said, it's like, well, obviously we're not going to zoom in, and these aren't even asymptotical limits. These are not asymptotical. I think this is what physicists have wrong, is that we should define these as asymptotical limits, but in reality they're actually not asymptotical limits. But you know, I feel like that's the only way we can do that, and that's why we don't really have to worry about renormal. Well, I can't really say anything because I don't really know what renormalization is, so I can't really say anything, which is something I have to think about more. And then, you know, I was reading quite a bit on Dirac, and then I was looking at manifolds, and I was like, what the heck are manifolds? And I was looking at that, and then manifolds are actually topological structures, of course, and basically they're topological structures, and they happen to be locally they can be Euclidean space, because if you take a curve and you zoom in and it becomes a straight line. If you think about, like, you know, a curving space, I guess, or whatever, like if you decide to, you know, so if you decide to curve space itself, then if you look really close to it, then obviously it looks like Euclidean space, which is why, I don't know, we humans see it as, I don't know. Yeah, so I mean, it's kind of like being on a sphere, right? If you're walking on it, that's why it took us a while to even realize that, you know, we're actually on a sphere and not on a flat surface. It took us a while. We had to look far and beyond to see it. So yeah, and since I was looking at manifolds, they call them homeological. I was like, what is homeological? I think that's what they said. Where did I find that? Topology, homeomorphic, sorry, not homeological. Homeomorphic, which are topological isomorphisms, and isomorphisms are seen in abstract algebra, which are homomorphisms. But they happen to be surjective and injective, and I believe injective is one-to-one, meaning that you have an object and only maps to that object, and surjective is it maps to all of that domain of a particular structure, if I can remember it correctly, or domain. It maps to all pieces of the domain. So you can think of like these structures as, I don't know, you can map these structures. It depends on what kind of structure it is, but I guess like a good way to think of it is you can look at R2 or something, and this R2 can be, you know, it has like what's a good surjective? You can think of like R1 to R2, basically. You're mapping the domain of R1, which is a line. R1 is just the real numbers, so they hold certain qualities. It's a structure. It's an algebraic structure, and R2 is basically just in 2 dimensions, basically. And well, I think x squared is a way of seeing it as an R1 to R2 mapping. I guess it's an R1 to R1 mapping, but also you can think of like x squared, right? So it's an R1. We could just simplify it and just keep it as an R1 to R1 mapping, and so I don't know. You can think of a cubic. Well, it's it may not actually. What's a good example? A line would probably just be the best example. Just a linear mapping, because I think cubics Do they kind of like curve downward close to 0? I know 0 obviously is your cube, but that's obviously negative because cubics can go to negatives and squares don't. But I believe cubics. I'm gonna look at it. Yeah, it loops down. So I mean, like if you look at 1, well, actually, it still maps the other way around. The inverse wouldn't be 1-to-1, I guess would be the right way to say. But I still think it's a 1-to-1 relationship. Even cubics would be that. Simply because each of these I guess there's like a domain and codomain, I believe. So the domain from the initial R1 maps to a codomain, and each of these objects from the domain gets mapped to each and every other object in the codomain, and they fill up the space. So that's why they're 1-to-1, because they don't map to 2 objects. So like if you take like 1 cube just goes to 1 object, and then if you look at like 2 cubed and all that, they go to 1 object. As if you look at like the function of a square roots don't always map to 1 object. Like if you take, they tend to have 2 each and every one, because it's plus or minus. Like if you take the square root of 1, it's -1 times -1, or +1 times +1. So it maps to two different objects. So it wouldn't be necessarily injective, but I believe it's surjective. Square roots are surjective. No, they're not surjective either. My bad. They're not, because they don't. I believe if you take in imaginary numbers, it would be surjective. I don't know. I don't really. My imagination isn't as good as it used to be, so I'm having trouble coming up with examples. But I wouldn't even say I don't think that would be either if you accounted for imaginary numbers. Maybe it would be, and then you can call it isomorphism. I don't know. I guess actually it would, because it would account for it. It just wouldn't be 1-to-1. I just know that if you account for the complex numbers. So you're mapping the complex numbers to another complex number, and you take the square root of that complex number. It goes both ways, of course. Yeah. But I think it would still not be injective. I believe so. I'd have to write that down. Yeah. So I was looking at that, and now I know what homeomorphisms are. I've never taken a class in topology before, though. So, like, a topology. I mean, there's just a lot of math that you have to study in physics. And topology is one of them, and I need to kind of look at the structure of what topology actually is, so I can have a better understanding of what they're trying to do with it and whatnot. But I could talk about like what I know from it, but it's very vague. Yeah, it's a good thing that I'm looking at some of these. But yeah, I have a good understanding of. Oh yeah, I was also looking at Lie groups. I just had to remind myself I need to understand what unitary matrices are, and I think these unitary matrices also can be unitary operators, because there's also unitary operators in these matrices. Maybe these matrices has unitary operators operating on these unitary matrices. I don't know what that is. But then you have Lie groups as well, and apparently Lie groups are also very important when it comes to studying manifolds, I think. There's something involving Lie groups. I forgot what the connection is with Lie groups. Oh yeah, I was looking at the special unitary group. Oh, what the hell? Oh yeah, right. Because the special unitary group, they use these notations a lot in group theory. It has, I think, that's what it's called, a group. It's a group that is essentially special unitary, whatever that means. I don't know, and I'm gonna look into that. But it pertains to Lie groups. So apparently it's a group that's a Lie group that happens to have some kind of just attributes that help out with physics that I just don't understand yet, because you have unitary matrices. I don't know, I think we talked about unitary matrices before. So they called the Lie group of unitary matrices. Okay. So some kind of transformation of some sorts. Lie group of unitary matrices. And it's also... Okay, so Lie groups are manifolds, which makes sense on why we're looking at these in physics as well. Oh, Jesus. What did I say about Lie groups? Yeah, they're supposedly differentiable, but they're differentiable manifolds because we want to, we don't like non-analytical mathematical structures, so we like to analyze them. They have to be differentiable for us to impose any kind of, well, derivative operators, I guess would be the right way to say it. They also have group multiplication and both group multiplication and taking inverses is also differentiable. So I really don't know what that means. I'm assuming that, this Lie group may contain these objects, and then these objects also have operators, and it's multiplication operators and its inverse. And I forgot, actually, now that I'm thinking about groups, they have one operator. They're not, these groups don't have binary operators. They don't have two operators would be the right way to say it. So you know how, an algebra does. Or I think rings also do, but groups are special. They only have one. So that's why you have the operator in inverse. So I guess it's binary, or it has two operators. I guess it is a binary operation, yeah. Yeah, so that's good to know. Good to know. Yeah, so I'm gonna look at Lie groups. I remember my teacher that I had for abstract algebra was he studied Lie algebras and groups and all that, and I don't know their importance in physics, so I don't have enough knowledge to really understand why they use these and why they study these groups. All I can say is that it pertains to a manifold, or manifolds. Or I guess they are seen as manifolds. Whatever that means. Topological surfaces that are differentiable, I guess. A lot of stuff. Or I meant to say topological surfaces that are locally homeomorphic. Isomorphic topologies, whatever that means. There's just a lot of different things I need to look at. I don't want to crack my head too much when it comes to this stuff because I've already been busy with a lot of other things pertaining to life and application. I did all my applications today, and I've been doing this in parallel and whatnot. But I can only jam so much information in my head. I can't absorb it like I wish my brain was like that, but it's not. So I had to take it a little bit slower. I don't want to go too fast. So, anyways, I think that's it. I don't really have anything else to say. Bye.